Okay, so this is Mr. Ye today. I'd like to go over how do I make this function continuous. So let's start with this function is a x plus 1 um, when it's x between 1 and 3. This is called domain restrictions. And this is another one is x squared plus bx plus c. In this case, the x squared is a variable, b is a constant, c is a constant. So here's a question. How do I make this function continuous by finding b and c the constant? So a lot of people have hard time understanding the problem with this. So let's start by kind of see what happened. Usually I will start by something that say, let's understand this piecewise function first. And the piecewise function says x plus 1 between 1 and 3. So I'm going to graph that x plus 1 between 1 and 3. So I'm going to show you what a graph look like. And then maybe you can go from there. So what I'm going to do is I'm going to go ahead and show you that function that looks like this part. And that function I'm going to show you here, it's going to look like this. So this function, but don't worry about the bottom part. So I'm going to show you the other function is x squared plus bx when x greater than 3 and when x less than 1. So I'm going to go ahead and click here and to show you that function. The function, the blue one, at one point is going to connect it to the red line. And then I'm going to show you the other one as well. So you see the black lines? At one point in time, that A's and B's going to equal the value they both connected. You see it's really fast. And you're going to see, okay, so which value I have to find for B and C and to make the function continuous. So the function is going to be continuous at one point where B and C is. So we're going to come back to this. First, let's understand the problem. So I will draw this. So I will first understand what a restriction means. So some type of restriction that I will probably graph something like if I have x plus 1, so it's going to be plus 1, and it's going to be like this, and this graph is going to be a straight line. So that's this part, okay? The other part is, what is the x minus 2 greater equal to 1? That's also restriction, but it's written in a way it's in term functions. So what I'm going to do is I'm going to rewrite this. I'm going to solve this by using absolute value inequality. So this absolute value inequality says x minus 2 greater than 1. And I'm going to solve what that x is equal to. It should end up to be something like this, some type of inequality. So we're going to go ahead and solve that absolute value inequality. So what we're going to do is we're going to split the two ways. We're going to take this. We're going to say x minus 2 greater than 1. And we're going to go with the other one. It's going to be x minus 2 less than negative 1. Okay. So I'm going to go ahead and solve it. This part is going to be plus 2 on both sides. So it's going to be x greater than 3. And this part is going to be x less than 2. So x less than 2 is plus 2 on both sides. So it's going to be 1. And if you realize that on this side, I just drop the absolute value. I keep everything the same and evaluate it. And with the absolute value, I'm going to change the inequality sign from greater than to less equal to, and change the sign to the other side. So I call it keep this part the same, change the sign, keep flip change, KFC. So that way that you can say, okay, this is how do I evaluate this. So instead of write those functions, what I'm going to do is I'm going to write in two different functions. One is a red function, which is going to be x squared plus bx and the plus c when x is greater than 3, greater or equal to 3. And at this part is going to be x squared plus bx plus c, and when x is less than 1. So I write it in this way. So what I'm going to do is I can cross out this information here, and I write in two different functions. So the idea is some type of red things here that hopefully is connected to here, and same parabola is going to go down and hopefully is connected to here. Okay, so the idea is we have to understand where is the endpoint on each piecewise function. So I usually look from the left to right. So from the left, the most left function is not this one. This one's the middle part. And this one is most to the right, which is the red part. And this one is less than 1, so I'm going to look at this part here. So I'm going to look at that part first. So what I'm going to do is I want to make sure when they reach 1, they equal to each other. Okay, when they reach 1, they equal to each other. Now let's talk about definition of continuity. We can talk about this a whole lot. What's definition of continuity? Okay, so what's definition of continuity? Okay, so definition of continuity is the first one is limit x approach to a from the left side of f of x equal to limit x approach to a from the positive side f of x. Second, and we're going to talk about this over and over again. So limit x approach to a of f of x. I'm going to start with first thing first is that f of a must be defined. F of a must be defined. 3 is limit x approach to a of f of x is equal to f of a. Okay, and that's how the function is continuous. So we're going to look at this. This is called definition of limits. F of a must be defined. Definition limit must equal to the same value of when it's equal to a. So we're going to talk about this side. We're going to assume this is some type of a first. So we're going to talk about between this third functions here, less than 1, and the second function. So in order for them to be continuous, they have to end up to be exact same points. So what we're going to do is we're going to using something called one-side limits. So we're going to approach this side, and we're going to plug in the correct equation. So what I'm going to do is I'm going to take a limit x approach to 1 from the left side. If I approach it 1 from the left side, which equation I'll be using? The first one, the second one, or the third one? Well, 1 from the left side, that means less than 1, so it has to be this function. So I'm going to say that's equal to x squared plus bx plus c is equal to limit x approach to 1 from the positive side. Well, 1 from the positive side, that means I'm going to use this middle part of the function. So in this case, it's going to be the x plus 1 function because that's the middle part of the function that has x plus 1, and we're going to plug in x plus 1. What I'm going to do is I'm going to also worry about this part. This part has to connect as well, but the endpoint is at 3. We're going to go in from the 3 from the left side and 3 from the right side. So what we're going to do is I'm going to do limit. And if you realize I was going from left to right, I'm going to kind of build a good habit. So 3 from the left side. So 3 from the left side, I'm going to use the x plus 1 functions because from the left side is including x plus 1 function. That's equal to limit as x approach to 3 from the positive side. Well, positive side, I'm going to use this function, the red function. So in this case, I'm going to color code this. It's going to be the red function. It's x squared plus bx plus c. Now, if you're going to say, well, what happened I didn't color code? Because this is both black right here. So we only in one, this one is different as this one is in red. So we're going to use this side of function just kind of show you what's going on. But what happened with limit is nice thing is you're going to plug in the limits. So what you do is plug in the 1 into the functions. If you plug in 1 into the function, you're going to get a nice, because probably it's just a constant. So what happens if I plug in 1? 1 squared, so it's going to be 1 squared. So I'm going to use the first functions and plug in the 1, use the limit approach method, plus a b and a plus c is equal to 1 plug in, so it'll be 1 plus 1, so this is 1 plus 1. And that's it. That's the first function. I'm going to do it to the second function as well. The second function is I'm going to plug in 3, so it'll be 3 plus 1 is equal to, what happened if I plug in 3 here? It's going to give you 9 plus 3 here, so it's going to be 3b, and then plug in 3 here, it's going to be still c because there's no variables here. So if you realize I only plug in the x3 squared and 3b, and c I just kind of leave it alone. Well, this nice thing is I'm going to go ahead and simplify this equation. This equation is going to be b plus c, and put a constant to the other side, so I subtract 1 on both sides is equal to 1. And I'm going to do, trying to get b and c together on one side, so I'm going to do 3b plus c is equal, I'm subtracting 9 on both sides because I want to move 9 to the other side. So 4 minus 9. What is 4 minus 9? 4 minus 9, that's going to be negative 5. So I got a system of 2 variable 2 equation. What's nice thing about this, if you have 2 variable 2 equation, then that's solvable. In this case, you're going to say that's a constant. Yes, it's a constant. We're trying to solve for that constant. But we're going to treat it like it's a variable for now. So we're going to solve for b and c in this case. The best way is I actually just multiply the first equation by negative 1. So I'm going to multiply that. I'm going to say that's negative b minus c is equal to negative 1. And then I just change this to here by multiply by negative 1. And I'm going to add, use the system equation. So it's going to give me 2b is equal to negative 6. And b is equal to negative 3. Once I find out what b is negative 3, I'm going to plug in the original equation. I'm going to say negative 3 plus c is equal to 1. So c, I'm going to plus 3 on both sides, so c is equal to 4. So in this case, I can find out b is equal to negative 3, c equal to 4. So I'm going to go back to use the decimal to show you what happened. So basically, you just plug in the value, but you're looking at the endpoints. But I'm going to show you what happened with limits and see what happened. So one side limits takes one side limit on both sides, and then we're going to show you. So what we're going to do is I'm going to do it on decimal. Decimal, we're going to set b is equal to negative 3. And so we're going to show you here. B is equal to negative 3 now. Okay, b is equal to negative 3. And c we're going to change into 4. But you see that it kind of makes sense. As opposed to before, I just let it play. It doesn't seem like, it seems like at one point in time they do connect each other. But it's really hard to fine tune that point. But as soon as I situate one side, right, we're going to change the b to, according to here, we're going to say it's negative 3. So if I do negative 3, and if I do c, I'm going to do 4. But I'm not going to, so I'm going to do c equal to 2 now. Just going to let it play it. So if I just do like this, you're going to see that it's one point they do connect because they kind of, that parabola is moving up and down. It's a parabola because of the gapping. So then you're going to see that c is going to, I'm going to try to manually do this. So we know c is roughly at 4, so we're going to pause roughly at 4. It's almost, that's past it, right? So we're going to go back. We're going to say that's 4, and we'll press enter. See this graph? That's connected, which is nice. Oops. Let's go back. X plus 1. And we're going to do that domain. X, it's 1. 1 less than x less than 1. 1 less than x 3. So you see that it's beautiful functions right here. And then the functions are all connected. Okay, you can see the function is connected. Now I'm going to show you here. And the function is connected. B is equal to -3, C equal to 4. Just like what we saw for B is equal to -3, C is equal to 4. We solve the problem using the definition continuous and definition limits, and we finish this problem. Okay, hopefully that can help you solve the next problem for you.